Welcome to CPE 350, Chapter 7, Binary Mass Diffusion, Example 13. We're going to cover gas diffusion in a solid. So the problem statement is about helium diffusing across pyrex glass. On one side of the glass, we're given a partial pressure of helium, and on the other side, there's a vacuum maintained, so basically no helium. And we're told that the situation is at steady state, and we're given some constants. We're given the diffusivity of helium in glass, which is also the diffusivity of glass in helium, but it's kind of strange to think about that. We're given the solubility of helium in glass, the density of glass, and the temperature of the system. So to sketch out what we're looking at a slab geometry. Helium is on the right-hand side in this diagram. I've drawn on a coordinate system because it's going to help us later, but the location of where I've drawn the coordinate system is arbitrary. It doesn't matter where you put it. And we have that species A, helium, is fluxing across the glass from the high pressure side to the low pressure side. So the question asks us for the steady state flux, which means we need to use Fick's law. The same way if a heat transfer problem asks for flux, we would use Fourier's law. So Fick's law is our constitutive law, and we have a choice. Do we use the form that has a weight fraction in it, or the form that has a concentration in it? And generally, the rule of thumb is that if there's a chemical reaction, you use the molar form with a concentration. But in this case, there's no chemical reaction, so we'll use the mass form. And that's what this is. And species A we'll define as the helium, and species B is going to be the glass. We're going to integrate Fick's law in our slab geometry by first separating the differential equation, so all the x's on the left-hand side, all the omega a's on the right-hand side, and I'm going to add the boundary conditions into the limits of integration now. You don't have to, but on the left-hand side, our x as defined goes from 0 to 100 microns, which is 1 times 10 to the negative 4 meters, and our mass fraction of A, we don't actually know what it is in the surface of the glass, so we'll just leave that as omega A naught, some value to calculate later. But we do know that on the far side of the glass, the concentration of A is 0 because the partial pressure is 0. So that also means the mass fraction is 0. Plugging through this, we're able to simplify the expression quite dramatically. And instead of carrying through that number 1 times 10 to the negative 4 meters, I'm just going to call it delta x, the thickness of the glass. So on the left-hand side, we need to find the mass flux of helium in the x direction, unidirectional. And now we're given the diffusivity and the thickness of the glass. What we need to calculate is this term rho omega A naught, which we don't know, but we have enough information given to us to calculate. So it's worth noting here that omega A naught is the weight fraction of helium that's inside the glass, just at the surface of the glass, that position x equal to 0. Be careful, we're working with a solid and a gas here. Omega A naught is not the partial pressure of A in the gas. It's how much helium dissolves into the surface of the glass. This is a little confusing because with solubility, you generally think of a solid in equilibrium with a liquid. And if you dump in more solid, the equilibrium concentration doesn't change. But the solubility of gas in a solid works slightly differently. So if you have a large partial pressure of helium, it drives more helium into the glass, and so the solubility increases at the surface and you have a greater mass fraction of A. Conversely, if you don't have a high partial pressure of helium, there's much less that dissolves into the surface, and so a lower value of that mass fraction of A at the surface. Again, the solubility here is not a constant value, it's something that depends on the partial pressure. So we need to quantify this value. We'll call it rho A naught, as we did before, which is just the density of A at a position 0, but it's not the pure species density of A, it's the density of A in the helium glass composite. And so to calculate that, what we need is the partial pressure of A written as a density just outside of the glass where the helium partial pressure is high. So I'm calling that rho A at a position x less than 0. And if we multiply that by the solubility we're given, which has units of volume of A per volume of B, you can see that these two cancel out and we're left with something that has units of mass of A per volume of B. This is not quite what we want for rho A naught. The units of rho A naught should be mass of A over volume of A plus B, the total volume. However, because we're working with a solid gas system, we can neglect the volume change of glass when helium enters it. Whatever volume the glass has, it's the same volume before and after the helium enters, to a really, really good approximation. And so that means that when we talk about the volume of B, we're actually talking about the volume of B plus A. And so this quantity is pretty much the quantity we're trying to calculate for rho A naught. We can use the ideal gas law to actually calculate rho A at x less than 0. And so we have the partial pressure of A, and what we need is the concentration of A. And so that's just the moles per volume. So we rearrange the gas law, and we have the partial pressure of A. We know what the ideal gas constant is, and we're given the temperature, and this is why we're given the temperature. So if we plug in those numbers, we get that the concentration of A just outside the glass is 24.1 moles per meter cubed. Now, to get this to a density, we just multiply by the molar mass of helium, which is diatomic, so it's about 4 grams per mole, and that gives us the density of A just outside the glass. Now we can plug this into our expression for rho A naught. So the density of A just outside the glass, it's kind of like the driving force, it's almost the partial pressure. We multiply that by the solubility of A in the glass, and we get that initial density of A just inside the surface of the glass at a position of x equal to 0. Finally, we're able to plug this into Fick's law and solve for the actual flux. So we have rho A naught, we're given diffusivity, and we know the thickness. For the diffusivity, remember to convert it from units of centimeters squared per second to meters squared per second. And we can just plug the numbers and get our final solution for the mass flux of helium in glass. Thank you for listening, and I'll see you for the next video.